Hello, everyone. Whoa, 500 people is a lot of people when you're staring at them. So let's talk a little bit about concurrency today. So for the purposes of this talk, I'm going to define concurrency as doing multiple things at sort of the same time. And it's something we use every time we interact with a computer, right? The fact that you can listen to music while you're starting your slide presentation means your computer is actually doing two things at the same time. And you can say, oh, of course, because my computer has multiple cores. And that's not necessarily true. You don't need multiple cores to do that. Computers were able to do multiple things for quite a long time. And that's because they basically they fake and they give a little bit of time to do different tasks. And for us, we perceive that as they being happening in parallel, but they're actually not. So if you ask a fellow Rubyist if they bother with concurrency, and you can ask that to the person sitting right next to you, you're going to get an answer that's probably going to fall down into 4 different categories. So the first category is going to be a resounding, yes, of course I use concurrency. My app runs on Unicorn or Fin or Puma or whatever. So there's a lot of Rubyists that for them, concurrency stops when they choose the right application server. It's something that a gem does for you. It's not something you do for yourself. The second group will be of course not. Ruby's not built for that. And there's a widely held belief that Ruby sucks at concurrency. And lots of programmers think why should I bother writing concurrent code if Ruby's going to do a poor job of running it? The third is the recently founded startup answer. It's who cares? I can spin more AWS instances. It's I can throw money at the problem and the problem goes away, which is the sort of answer that works until it doesn't, and then you have a big problem. The fourth answer is kind of a new one. It's oh, have you tried Elixir? So Rubyists that got tired of the previous 3 answers, they basically go to another language that has a better story for concurrency, and most of them have. So why? Why do we have such a shaky history with concurrency, considering that something is so ubiquitous? The first reason, I think, is kind of the elephant in the room when you talk about these topics with Ruby, is the GIL, the GIL, the JVL, the global interpreter lock. So that's something that's on the C Ruby implementation. You have a lock around the entire virtual machine that makes its code thread safe by blocking parallel execution. So to avoid having developers having to deal with concurrency issues, it basically disables concurrency, in a sense. And that's something that everyone knows, everyone talks about. Whenever you mention concurrency in Ruby, someone is going to say, but the GIL, but the GIL. But a little known fact is that it actually doesn't protect you from everything. It works only on the Ruby C code. And sometimes the Ruby C code has to go back to Ruby. For instance, when you're calculating a hash key, the Ruby C code has to ask Ruby for something. And when you cross that boundary, the locks go away. So it's still not, it's quite safe, but not 100% safe. And the second little known fact is that it is released during I/O actions. So Ruby doesn't keep the GIL while it's doing a HTTP call or a file read. So you can have concurrent I/O in Ruby, even though it has a giant lock. The second reason is that maybe because of this lock, Rubyists go towards forks, process forks. And forks are kind of a brute force approach of doing multiple things at the same time. It's basically if you want to do 2 things, you just have 2 copies, 2 entire different copies of that process you're running, and then those 2 copies can do 2 things. You want to do 3 things, you have 3 copies, 4 things, 4 copies, and so on. So it's a relatively safe strategy that's used by many Ruby projects. I think Unicorn is the most famous. And it's really safe on the concurrency side, because those processes really can't share memory. The OS protects you from doing that. But it's kind of wasteful on resources. Even with modern memory on write copy on write, sorry, optimizations, is still a little wasteful. Like, it tends to consume more memory, and it's also hard to coordinate work, because you have to use either like system calls or a message queue or something external to Ruby, because those processes, like, they don't know about each other. And like the third reason, and I think the main reason, is something that I think as a malady that I think afflicts all developers. It's called phylum phobia. Phylum phobia is described by Wikipedia as a irrational fear of threads. So really, who here likes threads? Like, I've seen a couple of crazy people here, but most sane developers don't like threads at all. And why? Because like, when you hear threads, you think about all those terrible things like deadlocks, impossible bugs, racing conditions, like that issue that only happened every other full moon, like those sorts of weird stuff. And you don't want to deal with weird stuff in your day-to-day job. And like, this is an excerpt from the documentation of the conditional variable class. I have no idea what it does, but look at that. It's terrible. Like, that sample doesn't do anything, and still has a lot of lines and noise, and if you miss one of those lines, the whole thing breaks. It's not a good experience. And the problem is, it's not exactly with threads, right? If you look at the thread API, it's actually quite a simple API. You do thread new, you pass a block. What's wrong with that? The problem is controlling mutable shared state. So when you try to have those two threads talk to each other while running at the same time, that's when you start to get into trouble. And like the tools that Ruby provides out of the box, like mutexes, conditional variables, monitors, all that sort of stuff, they're too clunky. They're not easy to use. Like, you have to know a lot about them. You have to be very careful. It's like coding in a minefield. It's not fun. But thankfully, there are more interesting models out there. Like, concurrency is not a problem exclusive to Ruby, of course. It's a problem that exists since computing exists. And there's a lot of hard thinking that goes into coming up with different models for dealing with that issue. And one of the models is actors. Yay. So a way to explain actors is like if you imagine like a normal object-oriented system, like any app, but with two very important differences. The first is that each object you have runs on its own like execution context. I'm using like a neutral term for threads, basically. So that those objects, instead of like a normal Ruby code where they all run in the same thread, each one has its own little space, its own little thing, and it runs there. The second important difference is that all method calls are asynchronous. Like, imagine programming without returning values. Like, you can't have a return value, you just send messages. If you have those two things in place, like each object running in its own space and asynchronous method calls, you have an actor system. And they look like an actor looks kind of like this. So we have the actor running in its context. It can have like its own state, and it can mutate that state if you want, like that. It belongs to the actor. And that actor also have a mailbox. And that mailbox acts like a little message queue. So other actors in the system are sending messages to this actor, and those messages, they go into the mailbox, and they get into that little queue. And then the actor is running on its own context, doing its thing. And when it's time to check for a new message, it goes into this mailbox and like, oh, there's a new message. I'll process this message. And during this message processing, the actor can do anything he wants, because that state is not shared. But if he wants to communicate with other actors, the only thing he can do is send more messages. So to give a little more concrete example, let's say you're developing an API or a system to compare like flight prices. So a message comes from somewhere saying like, I want to compare flight prices from Melbourne to Brazil. And like, I want to do this from this date to this date. So our system knows that if he tries to do that with just a single thread, it's going to take a while, because like finding those prices is hard. So he goes like, you know what? I'm going to spawn a helper. And it spawns one helper. You know what? I'm going to spawn two helpers. And it sends a message to one of those helpers saying, hey, please compare prices for this ticket for this subset of that big range. So if you ask the original system for 10 days, our actor A is just asking B to calculate 5 days. Because like the price for one day doesn't depend on the price of the other day when they're already calculated. So you can do that concurrently. And the cool thing here is that return to A field, which is basically A saying like, hey, when you're finished, send whatever you find to this address. And this address happens to be A, the sender, but could be someone else. And then it sends the same message to the other helper with another part of the range with the same idea, return to A. And like, I'm only using 2 helpers here because it's a slide. But you can imagine like this being done like with 10, 20, 30 different things. Like, it's basically, you could do this with as many different actors as you want. And when the actors are finished, they send the result back. So C says, like, oh, I finished. Here, I have the result. Like, for one day, it's 600. For the other days, it's that price. And B does the same. And then A, at that point in time, has the information to return the cheapest flight. And you see that the whole system is asynchronous, right? Like, A just sends the messages and waits for the messages to return. So you have to model your whole system around this idea that the information might still not be there. But still, it's a very powerful and very scalable model, even in slides. And there's no shared state. So all of those dreadful issues, they just disappear. Because those actors, they only communicate through messages. And those messages can't send like a memory address, unless you're cheating. Like, here is an array. Like, they can do that. It's just like very simple information. And an interesting thing you discover when you start reading about actors is that actors and object-oriented systems actually have a long history. So Smalltalk, like the first object-oriented programming language, or one of the first, comes out in 1972. And the actors paper, the first papers mentioning actors, comes out in 1973. And it actually mentions the Smalltalk as like an influence. So if you go to like one of the canonical OOP definitions, like someone sent Alan Kay, like considered to be the father of OOP, an email once, and I assume he gets this email like every other day, asking him like, oh, what did you mean by object-oriented systems? And he answered, oh, object-oriented programming to me means only messaging, local retention and protection and hiding of state, and extreme late binding of all things. Thankfully, they weren't using Slack, so we still have this message today. Sorry, Slack. And that, what it means is like you have the data, you have the state, and you have the actions that operate on the state, and they're very close together. But all the rest of the system is very dynamic, right? This extreme late binding of all things. And someone could say the same thing about actors. See? Like, you can pick any Alan Kay quote you want, replace object-oriented programming with vectors, and it's kind of true. So those two systems are very similar. And if you read the original actor papers, they don't talk about it as a concurrency framework. They talk about it as like a programming model. In the original one, as a programming model for artificial intelligence, but it can be for anything. Like, the idea is that you would like model your whole system as actors. Your processor would have actors instead of registers. It was a very bold idea, which is quite interesting. And it got popular in Scala with the Akka framework. Erlang, like, that's pretty much all actors. And now, Elixir. So what about Ruby? What does the Ruby ecosystem has to offer us if you want to like talk about actors? So there's currently like 2 active projects. One is called Concurrent-Ruby, and it's not just about actors. It has like definitions for all concurrency-related stuff you can think. And the other one is called Celluloid, which is the one I'm going to focus for this talk. So they're both they both started in 2012. And Celluloid has a strong following, lots of commits, lots of messages active, everything. And it works like this. So this is like an actor in Celluloid, and you see it looks very similar to any Ruby class, or any Ruby class in a slide. And the only difference is that it includes this Celluloid module at the top. And that's all you need. It turns like a normal object into an actor. The interesting thing is that when you call new on that actor object, instead of getting like a normal Ruby object, you get this proxy thing. And this proxy thing can still act as a normal object. So if you call methods on the proxy thing, it's going to behave just like a Ruby object. So in our case, since you have like a long sleep on our method, if you call process, it's going to take 10 seconds to do anything. But if you call async, and then you call a method on that async, you get the asynchronous messages. So in our case, nothing happens. Going back to our ticket prices, but now with Celluloid. So here's like a slide implementation of that idea of comparing prices. So you have this price comparator thing, which is not an actor. It's like a representation of a system. And initializes a bunch of workers. And it also initializes an aggregator to receive like the result of the operations made by those workers. And then it tries to treat those workers as sort of like a working pool. So it creates like a collection of those workers. And for each day in that date range, it asks for one of the workers to fetch the price. And that aggregator going out it's to represent the idea of that please return whatever you found to this address. There are better ways of doing that. And then if you look at the worker and the aggregator, they're pretty simple, of course, because slide code. But the worker could do any sort of complicated operation to actually fetch the price. So it could be scraping an airline site or calling APIs or whatever. But at the end of when it's finished, it sends a message to that address it got in the method call. So hey, I need to send my result back to aggregator. And aggregator is just waiting for those results. And in my simple silly implementation here, it pushes those results into an array. And whenever you call it, what's the current lowest, it goes into that array and oh, it's this one. And you could imagine a more realistic system having the information about, oh, I only have 2 days out of the 10 days I asked. So from those 2 days, this is the lowest, but that's all I can tell. But you can see that still looks a lot like Ruby, only with a couple of async calls and celluloids every now and then. But I think some folks in the audience are but what about exceptions? If everything is asynchronous, if something crashes, what happens? And how those actors get GCed? How Ruby deals with the fact that every actor has its own thread? That's crazy. So here is where the magic of conference slide code starts to fall apart. So you need to handle those actors yourself. And one of the tools Celluloid gives you is like a finalizer. So a finalizer is basically like a callback or a method that gets called when that object is about to get garbage collected. And on that finalizer, you can then later queue all the actors that object have spawned. So in our example here, that comparator, it's killing the aggregator and the workers. And it's killing by sending this terminate method that's defined by Celluloid. And that method takes care of killing the actors properly. But that's not good, right? Manually handling actors is not fun. If that was all that Celluloid has to offer, it would be better than threads and mutexes, but not much. You would still be a cool toy, but not an interesting application. But obviously, since I'm here giving a talk, you can't do much more. So Celluloid offers a bunch of stuff that are mainly inspired by Erlang's toolchain, the whole idea of letting things crash and restarting them instead of trying to keep exceptions from breaking your code. You basically okay, this one failed, next. So the first of these tools is linking. So linking is the idea of tying the 2 actors together. So you have here is a normal worker, and it has a sub worker that needs to do some part of the job, and that sub worker has a bug. Don't know how that got past code review. So when the worker asks the sub worker to do something, the sub worker breaks, and you can see on the Celluloid object that sub worker is marked as dead, and the next time you try to send a message to a dead object, you get an exception on the caller. But that's only going to happen the next time. So for a while, you have a broken system that you don't know about. And of course, whatever part of the work that you thought was happening is not happening. But you can fix that with a tiny little change. So instead of calling new, you can call new link. And that creates a link between those two actors. So whenever an exception happens in the children, the parent gets alerted by that exception. And if you don't do anything, the parent dies as well. So instead of having like a system that's half broken, you have a system that's entirely broken, but you know about it. So you can do something. And the place you do something about it is that you have this trap exit methods. And it's kind of like another callback that gets called when one of the linked actors crashes. So for instance, at this place, you could just restart the actor and just keep following along. Like you have a place to handle those failures. And you can like log, you can send a message to PagerDuty, whatever. But you have a place to deal with failures in your system. The second interesting thing is pools. So just like thread pools or connection pools, this idea that you have like a bunch of resources that look the same, and you want to treat that bunch of resources as the same thing, instead of having to deal with each individual. Celluloid has that idea, but for actors. So instead of calling actor new, you can call actor pool, and you pass that pool a size, or you can let Celluloid calculate that size from the number of cores your system has. And then you get this object that actually has a pool of workers beneath it. So every time you send it a message, you send this message to one of the free workers on that pool. And here, like, I'm representing that with the object IDs. And the cool thing is that Celluloid, you guarantee that that pool size is kept. So if one of the actors crashes on that pool, it gets a new one. So it tries to guarantee that there are always, like in this case, 5 actors running under this pool. And you can also terminate the pool easily. You don't have to go over each one and try to close it. If you tell the pool to terminate, it handles failure gracefully. The other cool thing is supervisors. So supervisors is the idea that you guarantee that one actor is always running. So again, like it is a theme throughout the Celluloid API. Most methods you call on the class of the actor. Supervise, you call it like on the class, and you give it a tag, or like a symbol in this case. Also the arguments that go into the initializer. And Celluloid is going to guarantee that there is a live worker under that tag in the actor registry, which is basically like a hash that lives in the Celluloid actor thing. It's going to guarantee there's going to be a live actor under that tag. So whenever you send a message to that address, there's going to be someone there to handle it. And if you combine that with the fact that you initialize workers, you can, like a parent worker can initialize more actors, you have a system that basically regenerates itself after every failure. And the final interesting thing is like Supervisor Configs. So Supervisor Configs, it's like a supervisor, but for the entire system. So instead of having only like one tree of parents and children, you can basically describe your entire system. And there's many ways of doing that in the Celluloid API. This is like the class-based approach. There's also like a hash configuration-based approach. But you have this class that inherits from this Celluloid supervision container. And inside this class, you have these methods to define like each type of actor. So you can say, I have this type of actor that's an aggregator, and you can also define pools. And for each thing you define, you give it a tag. And then Celluloid, you guarantee that under the actor registry, there is always going to be actors of that type to process work. And you can like boot up the entire system with run, you can terminate, and you have like this representation of your system, which is also pretty cool. So by looking at this, you might be thinking like, it's a bunch of constants. Like you have a giant hash. Where is that late binding of all the things? Alan Kay is disappointed. No, he's not. Because a really cool thing is that this system is actually live. So at any point in time, you can replace actors into that container. You can even replace actors with the same tag. So you can change the type of the actor. With the system running, messages flying around, for an actor of a different type, if you want, or a different implementation, and the whole system still works, because it's mostly, if you code it properly, it's mostly based on like those dynamic addresses. You don't have a lot of direct references to actors. So you still have all those messages flying around, and then you go and replace part of your system. And you can replace, if you consider that those actors usually come in trees, you have like a parent with a lot of children, you can replace huge parts of your system like that, while the system is still running. I thought it was pretty cool. And there is much more. This is just like an overview of the main interesting things, but like the library has a lot of stuff. It's actually a collection of gems. It's not all in the single place. And it's going through a bit of a revamp on its API right now. So some places in the docs, they reference the old code, but there's new code, but it's OK. It works. It's used by a lot of production projects. Like the most famous is Sidekick. And they also have a lot of interesting projects under the Celluloid umbrella. One is called like Nio4R, which is a Ruby version of the hipster Java I/O library, and it's pretty cool. It's like an evented I/O, and that's going to be used for Rails 5 in the action cable thing. You have dcell, which is the idea of getting these actors and distributing them across hosts, just like Erlang. So you could have like, instead of having this little actor thing on just your machine or just a server, you can model like entire systems in entire different hosts using the same abstractions, the same Ruby code with dcell. You have Real, which is an evented web server, so it's kind of like an event machine, but on top of Celluloid instead of being on top of event machine. And like a lot of cool, interesting projects under that umbrella. So another interesting Ruby concurrency theme that appeared recently, right after I sent this talk, proposal actually, Koichi Sasada, one of the most prolific Ruby implementators, announced he was working on a concurrency model for Ruby. And he called this concurrency model guilds. So from what I read, and I read just one paper, so I'm not a specialist on guilds, it's kind of similar to the actors idea, where you have like these things running on their own threads, and those threads have a strict communication around them. But instead of talking about sending messages, it talks about transferring object ownership. So it's like you teleport objects from one context to the other context. It's like, I'm really glad that Ruby is finally possibly getting its own concurrency model. I think it's really cool, but it might be part of Ruby 3. It's still like a proposal, and Ruby 3 is still a little far off. So for a long while, we will have to keep living without a proper Ruby concurrency model. So concluding, concurrency is hard. There's no way around it. Like I could claim, oh, it's just like Ruby, but that's not true. You still have to handle a lot of niche cases. But it can be much better than instantiating mutexes and semaphores. The way the Ruby community totally ignores it, it's getting embarrassing. Like my Wi-Fi scale has multiple cores. Like there's no way to keep pretending it will go away, because it's not going away. And the amount of resources we currently waste because of that is pretty embarrassing. Celluloid is obviously not Elixir, it's not Erlang. A library will never be able to compete fully with like a whole language developed around the concept. But maybe it's good enough. Like I'm assuming everyone here is in a Ruby conference because they still like coding Ruby. And you can have lots of those cool toys that are in Elixir in your Ruby code. And you don't need to replace your Rails app with vectors, right? No one is going to actually do that. But maybe those background jobs you have, those microservices, all those like upload things and import things and download things, those side tasks that consume so much of our time, maybe they're a good target for these things. Maybe there are like interesting ways of starting to toy with these ideas. That's it.
Well, I'm very disappointed that I haven't learned anything new about acting. That was fantastic. Thank you so much. So I think we're going to do a bit of Q&A. Have you got the app up, Mel? Because I managed to leave my phone downstairs.
It'll just take a second.
I'm really clever like that.
Oh, sorry. I can't work my phone.
Technology, right?
How does it work? All right, hang on.
Maybe I'll get my phone, and in the
No,
meantime...
I can do this. All right, we got it.
Excellent.
If your company already had an Elixir in use, would you still choose Actors or Celluloid and Ruby?
Depends. Do you want to use Ruby? Of course, like I said, Elixir Erlang's implementation, it's always going to be more mature than any Ruby gem. There's no way around it. So if you're already using actors in like Erlang or Elixir or Scala, unless you really want to use Ruby, there's not much of a point. But if you're not, that's where the Celluloid plays in.
Cool. How, in the Erlang VM, actors can execute in parallel, but as you mentioned, we've got the GIL in Ruby. How useful are actors without true concurrency? So, like, if you're doing something that's entirely, like, CPU bound, not much. You still can use JRuby, and then you don't have the JVL. But the thing is, a lot of stuff we do is actually I/O bound. A lot of stuff is downloading files, sending API requests, and that sort of stuff. And that's where you can use actors for good effect in Ruby. Like, until or you go to JRuby, but until the lock is removed, you're never going to be able to have true concurrency, true. But you can still do a lot with just concurrent I/O.
Sorry. What font did you use in your slides? We're just curious.
Font Leroy Brown and Belarus.
It was lovely.
Mm-hmm. That was a great question.
The Belarus is terrible to work with.
Which do you find better Which do you find better from a usability and performance perspective, Celluloid or Concurrent-Ruby? So, Concurrent-Ruby has a lot more concurrency paradigms than just actors. The actors are still listed as an edge feature, and I'm not sure if they're being listed as an edge feature for a while. I'm not sure if there's anyone actively looking into promoting them to not edge, I guess, to stable. So I would prefer Celluloid just because it's all about actors, and it's been going for a long while all about actors. They're both really nice. I think both APIs are really cool. And you're probably gonna, they have little differences, subtle differences in the way they handle things. So the decision is probably gonna come more from those little things than from just UX, like developer UX, because at least I find both APIs to be quite useful.
And one final question. How much of this actor pattern, etc., is used at Culture Amp?
So Culture Amp uses Elixir for a bunch of services. So the Celluloid part, not much, but on the Elixir part, yes. And most new services we're extracting for good old Rails monolith are probably going to be written in Elixir.
Cool. Thank you so much.
Thank you.
That was awesome.